Now that we've been looking at exponential functions and how to simplify them, we're going to look at how to solve them. Solving and simplifying are very, very similar. And when I'm solving exponential equations, so equations that involve exponents with same bases, I'm going to use this theorem here that exponential functions are one-to-one. So that means that I cannot have two exponential expressions being equivalent unless my exponents are the same. This is kind of the big thing we're going to use. If we already know the bases are the same, that tells us the exponents have to be the same. So we'll start by looking at a couple examples. I think there's two where the bases are the same, and then we're going to look at some examples that are a little bit more higher level difficulty because my bases are going to be different. So the first example, I see my bases are the same. So if I have base 4 to the x plus 2 equals base 4 to the 4x minus 3, the only way these two sides can be equivalent is if x plus 2 is equal to 4x minus 3. This is a basic linear equation, very basic to solve, so I'm going to go ahead and get my variable on only one side. Get rid of add or subtract. And then get rid of multiply or divide, giving me x equals 5 over 3. The second example is very similar to the first in the aspect that it already has same bases. But notice that my equation that I'm going to come up with when I set my exponents equal to one another is a little bit higher level. I get 5x minus 6 equals x squared. I cannot square once I'm up in an exponent, so I do have to use that caret for my notation. From here, hopefully you realize that this is a quadratic equation, and therefore I want to get it equal to 0, so I can either factor or use the quadratic equation. I think it's weird to have a negative on my quadratic term, so I'm going to go ahead and get everything to the left, and I get 0 equals x squared minus 5x plus 6. I'm going to go ahead and try to solve this. So first thing I notice is that I can factor this to be x minus 3 times x minus 2, since negative 3 times negative 2 multiplies to be 6 and adds to be negative 5. If I then set each of these pieces equal to 0, I get either x minus 3 equals 0 and therefore x equals 3, or I get x minus 2 equals 0 and therefore x equals 2. Those are some examples where my bases are the same. All I have to do is set my exponents equal. Now let's look at when our bases are not the same. So a little bit higher difficulty level. What we want to do is we want to make or manipulate one of or both of our bases to make sure I want to make sure to get the same bases. We want to be careful that we do not change the value of the base when we do that. So let me show you what I mean in example 1. So in example 1, I see my bases aren't the same. So typically what I see students struggle with is, do I make this 3 squared, or do I make this 9? Or do I make the 9 3 squared? Well, if I try to change the left side to 9, if I rewrite 3 as 9, notice 3 does not equal 9, so I cannot magically change the 3 to a 9. Also, 3 does not equal 3 squared, so I can't try getting it to be 9 through that route. If I look at the base on the right side, however, if I were to look at 9 and say, couldn't I change that to 3 squared to get a base of 3? If I ask myself, is that still equivalent? That is. So if I were to change this 9 to 3 squared, it would not change the value of my equation. I would have 3 to the 5x minus 8 equals 3 squared raised to the x plus 2. Well, I remember from back in Algebra 1 that if I have power to a power, I multiply my exponents, so that gives me 3 to the 5x minus 8 equals 3 to the 2x plus 4. Now that my bases are the same, I can go ahead and set my exponents equal to one another and solve this linear equation. So I'll start by subtracting the 2x. So 3x minus 8 equals 4. I'll then add the 8, giving me 3x equals 12. Dividing by 3, I get a value of 4 to make the left side equivalent to the right side. Now would be a good time if you wanted to try 2 or 3. On example 2, so this is the same thing as 1 over 16 to the x minus 3 equals 4 to the x plus 2. So once again, I go through the dilemma of, do I want to change a 16 to a 4 or a 4 to a 16? Well, changing 4 to 16 would change my value. However, if I just wrote 16 as 4 squared, that does not change the value of my equation. Then I notice that this 4 is in a numerator because technically there's a 1 under it, whereas this one's in the denominator. So I want to move this one up to get that in the denominator as well, thus making my 2 negative. And now finally I can say, hey, I can distribute that minus 2 because power to a power I multiply. Oops, I forgot my x. So I'll have 4 to the negative 2x plus 6 equals 4 to the x plus 2, which means negative 2x plus 6 equals x plus 2. I can now solve this linear equation. I'll add the minus 2x. I'm not going to show my steps here because I'm running out of room. Subtract 2 and divide by 3, and I get 4 over 3 equals x. Finally, looking at the last example, if you did not try example 2, please do make sure you try example 3. Excuse me. So let's see. So I look at 27 and I look at 9. My initial reaction is to say, hey, maybe I can like square 9. Oh no, that gives me 81. Maybe I can raise 27 to the 1/2 power. I have no idea what that is. So I think about it a little bit longer and I realize, hey, 27 is 3 cubed and 9 is 3 squared. So what if I change them both? What if I change them to give me 3 cubed to the x minus 1, since 3 cubed is the same thing as 27, equals 3 squared to the 2x minus 3, since 3 squared is the same thing as 9. Again, I apply my exponent rules, giving me 3 to the 3x minus 3 equals 3 to the 4x minus 6. And then say now that my bases are the same, I can say 3x minus 3 equals 4x minus 6. It's linear, so I'll start by subtracting the 3x from both sides. Again, I'm not going to show my steps since I'm out of room. I then add 6, giving me x equals 3 as my final answer. So big thing is, once you get your bases the same, go ahead and set your exponents equal. Remember, if you have power to a power, you multiply. And remember that when you're manipulating your bases, you want to make sure you don't actually change the value of your base.